Welcome to Brunda Engineering Academy. In this video, we will continue the subject material science. In that material science subject, testing of materials concept. This testing of materials concept will be mainly helpful in competitive examinations, that is RRB, ECET point of view, GATE and APPSC. In this video, I will discuss and explain about only the keynotes and shortcuts utilized for the used for the competitive examinations only. So first, testing of materials. Testing of materials means in engineering applications we are using different engineering materials. So that materials can be tested in the two different ways. One is destructive test. One is the destructive test. Destructive tests. Destructive test means the material can be definitely damaged. We should apply some forces on the material. Then definitely the material will be disturbed. The structure of that material will be disturbed. This destructive test can be used to find out the strength of the material. Please understand, this destructive test can be used to identify the strength of the materials, mainly strength of the materials, to determine the strength of the materials. Due to this destructive test, the material will be completely collapsed. Next, the second test is a non-destructive test. NDT. NDT means non-destructive tests. Non-destructive tests. That means in this test there is no damage to the materials. Non-destructive, as the name indicates, the materials cannot be the structure of the material cannot be disturbed. It can be used to find the internal defects of the material. Internal defects of the materials and surface defects also, for the finished products. So destructive tests can be used to find the strength of the material. Non-destructive tests can be used to find the internal defects and surface defects involved in the any type of materials. So now, first let us discuss about the destructive tests. That in the destructive tests, the major important is tensile test. Tensile test. Tensile test. This test can be conducted by UTM. This test can be conducted by the machine. Equipment name is UTM. UTM means Universal Testing Mission. Universal Testing Mission. UTM means Universal Testing Mission. So, tensile test can be conducted by Universal Testing Mission. By using this Universal Testing Mission, we can find out the different types of tensile properties. What are the tensile properties can be measured by Universal Testing Mission? Or one is yield strength. Yield strength also can be found out by using Universal Testing Mission. Next, letter percentage of elongation. Percentage of elongation. Elongation is nothing but the change in dimensions or change in length. Percentage of elongation can be found out by using the Universal Testing Mission. After that, Young's modulus of the material also find out. Young's modulus. Young's modulus. Young's modulus is nothing but it is the ratio of the stress and strain of the material. Stress and strain of the material. That already we discussed in the previous videos. That are mechanical properties of the materials. Next, another property, that is fracture toughness. Fracture toughness. Fracture toughness. Fracture means it is the failure of the material. That is, fracture toughness can be measured by using the universal testing machine. And another is resilience. 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 Resilience properties also can be calculated by using the universal testing machine. So these five type of properties, that means these are the tensile properties, that all tensile properties can also be measured by using the universal testing machine. Now generally in any type of machine we should prepare a specimen. Okay, in the universal testing machine the dimensions of the specimen or the shape of the specimen will be like this. In the examination point of view also they may be asked this question. Okay, here this is the specimen. The specimen having different dimensions. Here in this way we have the specimen. Roughly I am drawing. So this is the actual shape of the specimen. Here this specimen length, it is called as the parallel length. The parallel length, the standard dimension of this is 57 mm. 57 mm. It is the parallel length of the specimen. Parallel length of the specimen. And here the specimen having the diameter, its diameter is, that specimen diameter is 12.5 mm, that is plus or minus 0.25 mm. Some tolerance will be considered here. So here it is the parallel length. It is called as the parallel length and it is the diameter of the specimen. And again we have the gauge length. Gauge length means here the major portion. It is the gauge length. It is the gauge length. Now the gauge length of the test specimen in the universal testing mission is 50.8 mm. It is the gauge length. It is the gauge length and it is the parallel length. Parallel length. So this is the details about the test specimen. Test specimen. Next, after that, we have two different types of stresses. One is the normal stress. Normal stress is nothing but engineering stress. And here we have stress and another one is the strain is there. Stress means load by area, we are already discussed. Strain means change in length by original length, change in length and original length. Next coming to here one important notation, that is true stress. What is meant by true stress? True stress, it is important one. The definition is, it is also a stress determined by instantaneous load acting on instantaneous cross section area. When the load is acting instantaneously, then that corresponding stress is called as the true stress. That corresponding strain is called as the true strain. Observe the difference, true stress and true strain. The definition is, I am not writing here the definition. True stress means stress determined by instantaneous load acting on instantaneous cross section. It is the cross sectional area. On this cross sectional area, if the load is acting, then that corresponding stress is called as the true stress. That corresponding stress is called as the true stress. That corresponding strain is called as the true strain. Okay, so that is about the true stress and true strain. Next, of coming to the formulas point of view, the true stress, true stress equal to 1 plus 1 plus engineering strain. Engineering strain, this is the engineering strain, that means the normal strain into engineering stress. Okay, it is a sigma E and it is E small e. So this is the true stress and true strain. Okay, so this is the true stress. Next, coming to the true strain. True strain equal to ln of logarithmic function of 1 plus engineering strain. So these are the two important relations, true stress and true strain. In the gate examination point of view, they may be asked the problems on this point, true stress and true strain. If the instantaneous load acting on the instantaneous cross-sectional area, then that stress is the true stress, that strain is the true strain. Okay, true stress is 1 plus normal strain into strain. And here these two are the relations, and they may be asked the problems also. Next, another thing is here percentage of elongation, percentage of elongation percentage of elongation is, suppose if you observe this diagram, if you apply the load, the tensile load in this way, if you apply the tensile load, then initially it is having some length, it is having some length L0, it is actually original length, original original length. And after the applying the load, after applying the load will be the length will be changes, that is called as the final length. Final length is taken as the LF. So the percentage of elongation, the percentage of elongation, how can you calculate the percentage of elongation? Percentage of elongation is LF minus L naught by L naught into 100 percentage. Okay, percentage of elongation is change in length by original length, actually. Change in length by original length into 100%. Change in length means final length minus original length by L0. So here it is the percentage of elongation. If you apply the tensile load, if you consider, if you apply the tensile load in this way, then what will happen? Its area will be reduced. So then we can find out the percentage of reduction in area, percentage of reduction in area. In the RRB examination point of view, these will be important. Percentage of reduction in area. Reduction means original area will be more and final area will be less. So A0 minus AF by A0 into 100 percentage. So percentage of elongation is this one and percentage of reduction in area will be this one. Next here L0. L0 is actually here gauge length. L0 can be taken as the gauge length. Gauge length is nothing but the original length of the specimen. Original length of the specimen. We are having two different formulas. That is L0 equal to 4 into square root of A0. It is the worldwide formula. Whereas Indian specifications L0 equal to 5.64 into square root of A0, square root of A0. Observe the difference. Whereas it is the Indian standard specification, IS specification. As per IS specification, gauge length can be calculated by using this relation, that is 5.64 into square root of A0. Whereas in the normal terminology, that is L0 equal to 4 into square root of A0. Okay. Next, based on this percentage of elongation, we can decide the ductility. Okay. So we already discussed about the ductility matter. Ductility. So ductility measurement. The next property is the ductility measurement. Ductility measurement can be calculated by using the percentage of elongation, elongation in length. Ductility can be measured in this way, or percentage of reduction in cross sectional area, percentage of reduction in cross sectional area of the specimen. So ductility can be measured with this relation. Now in the competitive examination point of view, observe this bit, that is ductility of the material at lower temperature is less than ductility at room temperature. Ductility of the material at lower temperature is less than the room temperature. and that will be less than the higher temperature. So finally what we understand, at the higher temperatures ductility is more, at the lower temperatures ductility is less. It is an important bit. Ductility at lower temperature is less than ductility at room temperature, is less than ductility at higher temperature. What is the sequence of order of ductility at low temperature, room temperature, and higher temperatures? Then we can remember this. At the higher temperatures, the ductility is having more value. Okay. So next we have stress strain diagram. So from the stress strain diagram, we can measure fracture toughness. Fracture fracture toughness. That fracture toughness can be measured by the area under area under area under up to failure point, up to failure area under failure point in the stress strain diagram, stress strain curve. Okay, area under stress strain curve up to failure point. Fracture toughness is the area under stress strain curve up to failure point. Okay. Next another one is the resilience measurement. Resilience measurement can be it is also the same. Area under stress strain curve up to elastic limit. Please remember these 2 points. Area under elastic limit in stress strain curve is the resilience. Area under stress strain curve under failure point, under up to failure point is the fracture toughness. Fracture is nothing but the failure. So that's why failure toughness is under up to the point of failure point is the fracture toughness. Up to the area up to elastic limit is the resilience. Next this in this way we can measure the resilience property. Next another one is the compression test. Compression test is also conducted by using universal testing mission only. Okay, universal testing mission only. Okay, please remember that bit. As per the concept, only this point is noted point. And another is important point in the competitive examinations, izod test. Very important. Izod test and charpy test. Izod test and charpy test. These two tests can be used to measure the impact strength. These two tests can be used to measure the impact strength of the material. Impact strength of the material. So in the izod test, what they ask in the competitive examination, the test specimen is mounted as the simply here in the izod test, the test specimen is mounted as the cantilever beam. Cantilever, cantilever, cantilever beam. The test specimen is arranged like this. Suppose it is in this way. We will arrange the test specimen. In the izod test, the test specimen is arranged in the cantilever beam. Whereas in the charpy test, the test specimen is arranged in the simply supported beam. Simply supported beam. In this way, the test specimen will be acted. Okay, observe, it is a very important point in the competitive examination point of view. The arrangement of the test specimen in the izod test is cantilever beam form, whereas in the charpy test is in the simply supported beam form. Okay, next impact strength. What is the relation to find out the impact strength of that material? Impact strength is nothing but the energy absorbed when the sudden load will be acting. So the energy absorbed or impact strength can be calculated by W into H1 minus H2. Here W is the load acting on the test specimen and H1, H2 are the distances. Okay, so here in terms of the kilojoules, so impact strength is W into H1 minus H2, H1 minus H2. Okay, next coming to the hardness test, hardness test. Hardness test is nothing but, suppose we are considering a test specimen like this. On this, we will act the some load will be acting at a point. Some indentation will be acting there. So in the competitive examination point of view, there are three types of hardness tests are there. One is the Brinell hardness test. The Brinell hardness test Brinell hardness number is 2p by what in relation pi d into d minus square root of d square minus d square minus d square. So here p is the load acting on the body, p is the load acting on the material. Next, D is the diameter of the indenter, and a small d is the diameter of the indentation. Observe the difference. Indentation. So the Brinell hardness number is given by 2p by pi d into d minus square root of d square minus d square. Okay. So the capital D is the diameter of the indenter here. Next, indenter is nothing but it is a metallic ball in the spherical shape. Okay, it is having some diameter. Generally, it is having nearly 10 mm like this. Okay, next, diameter of the indentation, that is the mark formed on the material when we apply the load. If you apply the load on the body, some indentation will be acting on the body. So that diameter can be measured here. So based on these two, diameter of the indenter and indentation, we can calculate the value of the Brinell hardness number. Next, coming to another method, that is Rockwell hardness test. Rockwell hardness. Rockwell hardness. Rockwell hardness test. Rockwell hardness test, that is RHN. So here Rockwell hardness test, majorly it can be used in universally. It is the universal method. Indenter can be acted as the indenter can be acted as the penetrator means it can be make a hole. The suppose it is the body, then the indentation or it will be penetrated towards the body, into the body. Okay, so here in the Rockwell hardness test, we will use the diamond cone can be acted as the indenter. And here its apex angle, it is important bit. The apex angle of indenter used in the Rockwell hardness testing machine is 120 degrees. Okay, diamond cone can be used as the indenter in the Rockwell hardness testing machine, and its apex angle is 120 degrees. It is very clear. Next, if you observe in the Rockwell hardness testing machine, we have two different scales. That is the Rockwell hardness testing machine B scale. Okay, one is the B scale. It is in the form of red color. Okay, Rockwell hardness number on B scale. That B scale is in the red color. Okay, it can be used for the soft materials. Red scale or B scale can be used for the soft materials. For to find out the hardness of the soft materials, we are using the Rockwell hardness testing machine B scale. Now, the what is the relation? The Rockwell hardness testing machine B scale is 130 minus D by 0.002, and D is the depth of the penetrator. D is the depth of the penetrator. Please remember, D is the depth of the penetrator. And the number of divisions on the B scale is 130 divisions. Number of divisions on the B scale is the 130 divisions. Next, coming to the Rockwell hardness testing machine C scale, another scale is there, that is C square. It is in the form of, it is in the color of black scale, and it can be used to measure the hardness of the hard materials. So for the soft materials, we are using the Rockwell hardness test B scale, whereas for the hard materials, we are using C scale, and the formula for the Rockwell hardness number is 100 minus D by 0.002. The number of divisions on the C scale is 100. The number of divisions on the C scale is 100. So this is the complete data about the Rockwell hardness number. So the theoretical bits are very important in the competitive examination point of view, and they may be asked some simple problems using these relations also. And another method is also there, that is the Vickers hardness test. Vickers Vickers hardness test. Vickers hardness test. It can be used to find out the hardness of the medium hard materials. Medium hard materials. And here indenter is in the shape of it is a diamond of a square based pyramid. Diamond of a square based pyramid with apex angle. Here not apex angle, it is the included angle. The included angle of indenter. Included angle of indenter is 136 degrees. Okay, between the opposite faces. The included angle in Vickers hardness, included angle of indenter is 136 degrees in Vickers hardness test. The Vickers hardness test Vickers hardness number can be calculated by 1.854 P by D average. P is the load acting on the material, and D is the depth of the penetration. D is the depth of the penetration. So these are the different destructive tests to measure the strength of the materials majorly. Next, coming to the non-destructive tests. Very simple thing we can remember easily. Non-destructive test. Non-destructive test means one is visual inspection. Visual inspection means it can be, the defects can be observed with our naked eye. Okay, so that is the visual inspection. So what can be measured? What can we observe the finished product? The surface defects can be observed. Surface defects can be observed with our naked eye, and dimensional accuracy. This is dimensional accuracy. Please note it in our notes. Dimensional accuracy can be observed by visual inspection. Surface defects also measured by the visual inspection, and penetration in welded joints. So that can be also observed by using visual inspection. Just NDT, non-destructive tests, can be used to find the or identify the different defects involved in the material. Okay, next another one is penetration test. Okay, now I'm stop this video here. In the next video, we will discuss about the non-destructive tests. Okay, very clearly. So these are the different items, different concepts involved in the destructive tests. Okay, in the next video, we will discuss about the what are the non-destructive tests. So I discussed in this video in the competitive examination point of view only. Okay, the major formulas and what are the different definitions we are discussed. If you like this video, please subscribe Brunda Engineering Academy channel. If you have any doubts, please mention in the comment box. And if you missed the previous topics, that is what are the different mechanical properties of the materials, that will be also available in our Brunda Engineering Academy channel. So thank you.